Hello everyone, welcome to this online course on material science. This is lecture 7 in module 1 on magnetism. In this lecture, my plan is to start discussing about some of the basic concepts in quantum mechanics to understand magnetism. To start, let me state the postulate 1, which says a quantum mechanical state of a system is defined by specifying a ket vector psi which lives in a Hilbert space. So there are a number of informations in this postulate. The first thing that I want to say is that the system can be anything, right? For example, it can be an electron moving in a free space. It can be an electron moving around a proton in the hydrogen atom. It can be the entire hydrogen atom, right? It can be that an atom with tens of hundreds of electrons, right? So depending on your problem, the system can be a different thing. That's one thing I want to say. And then every system is denoted by this angular bracket, which is known as the ket vector. So anytime you see a structure like this, that's a ket, inside you can put some label to denote what the quantity you're referring to. For example, if I write a phi here, it's a phi ket vector, right? If I write, say, x ket, that's the position of a particle, maybe x, right? So that's the position ket vector. If the particle in 3 dimension, maybe it's moving, and x, y, z, we need 3 coordinates to specify the position of the particle, then we can write the label vector r to say it's the position vector ket for a particle in 3D, right? So it can be many things, the labels inside the ket, depending on your problem. So the central message is every ket denotes a state of a quantum mechanical system. So these are the ket vectors. Once you have a ket, the next important thing to know that for every ket vector, for every ket psi, let's say, we have a corresponding bra vector. And if you see the notation of the bra vector, it's like the angular bracket but pointing towards left, right? Why we need a bra vector, this will become clear in a moment, but physically you can think that, let's say we have some space, right, a Hilbert space, where all the kets are living, right? For example, we have a ket like phi ket, another ket maybe it's a psi, another ket maybe it's an x, so there are many kets in this space. We have to think of that there is a dual space to this space where every ket has a corresponding bra vector. So that's the ket vector, that's the corresponding bra vector, right? So for the psi, it should be something like this. For the x, it should be x bra vector, right? So you have ket vectors, you have bra vectors. Now, the question to ask is that what to do with these vectors? In quantum mechanics, one important quantity of interest is known as the wave function, right? And I will explain about it in the next lecture. But here, the point I want to make that once you have a state, then the next question is, what is the wave function of that system? How to derive the wave function from the given ket? That's where these bra vectors become handy. Because if you remember, you're trying to get a function out of a vector, and the function produces a fixed number for a fixed r, right? For example, if r is fixed at some point, then this is just a number. So you are trying to get a number out of a vector. If you recall in your vector calculus, one way to get a number out of a vector is at the dot product, if you remember, right? So let's say we have a vector in 2 dimension. For example, let's say it's 2i, I is the unit vector along the x-axis, and 2j, j is the unit vector along y-axis. So if we form a dot product with the vector itself, then you know this will be a number, right? And you know how to do the perform the dot product. It's pairwise product of components and then add it. So we have 4 times 4, which is 8. So we are getting a number out of a vector. The similar concept are Similar concept is used in quantum mechanics, right? So you need to form an inner product of a ket vector and a bra vector to make a number. Let's say we have some ket, I don't know, maybe it's phi, and we have another, it's a bra vector, right? Sorry, it's a bra vector, and we have some ket, I don't know, maybe it's a psi, right? You can define an inner product between these two vectors. So inner product has to be defined between a bra and a ket, always. You need one bra vector and one ket vector. And usually the notation is like, so you have a bra here and you have a ket here. So that's a notation for inner product between a bra vector phi and a ket vector psi. You can see this form a bracket, right? So bra and ket. This notation was invented by famous physicist Paul Dirac. That's why we usually call this notation Dirac bracket notation, right? So you have a ket vector. If you perform an inner product, you get a number. And we will define these things in more detail, but at this stage, I want to use this inner product concept to find out our wave function, right? So let's say now we have some state or some system psi, and from this we want to know what is the wave function, and I'm assuming the wave function is a function of three-dimensional coordinate, right? Let's put the position x, y, and z. How to get this number out of this vector? The idea is that you have to find the bra vector to make an inner product with the psi, and the bra vector to use, it turns out to be the vector, the bra vector position r. So this is an inner product between the position bra vector r and the ket psi. If you perform this inner product, the number pops out is the wave function. That's how you get a wave function out of a ket vector. That's very important, and I put them in a box so that you remember this quantity. I want to make a comment about this argument here. Usually the wave function can be more complicated. It can depend on like x, y, z, which is the three-dimensional position. It can depend on time. It can depend on the spin of the particle. So it can be complicated. But for our purpose, we are assuming that the time and the spin part we don't care right now. We only care about the spatial variation of the wave function. And the reason will become clearer later in the lectures. Okay. So postulate 1, we have some understanding about this. Now let me state the postulate 2, which is about the operators. So it says every physically measurable quantity, let's just denoted by A, can be represented by an operator A hat. So you have to put an hat to represent that it's an operator. Example, right? Let me give an example first. So in a classical system, energy of a system is measurable, right? You can measure the energy of a system. So this E in quantum mechanics will be represented by E hat. You have to put the hat to denote that this is an energy operator. What are the other physical quantities of interest? Usually, say x, the position of some particle. You can measure it, right? In quantum mechanics, you have to put the hat. So every time you see some physically measurable operator, the physical measurable quantity, in quantum mechanics, you just put some hat to denote that that's an operator. But a crucial difference, you have to remember that these operators do not have any value associated with it. For example, just to illustrate this fact, ddx is an operator, right, in calculus. The operator operates on something, but as an operator, it doesn't have any value, right? Similarly, the energy, the physical quantity in energy has a value, but the energy operator does not have any value. Then the question is how to produce the value of an operator. It turns out that we need to perform a calculation which is called the expectation value. So the expectation value of the operator is the value of that operator given some state. But I will discuss about this expectation value in the next lecture. But here, remember, the operator does not have any value associated with it if in its raw form, right? Okay. Now let me give you some examples of operators that are available that will become handy in studying the diamagnetism, right? Usually the diamagnetism or the atomic diamagnetism is due to the electron motion, right, inside the atom. So the position of the electron will be important, and so we have position operators. For example, let's say we have some three-dimensional space. This is the center, the origin, and then electron is moving in some paths. So we have some position vector r. So this r will be an operator denoting the explaining the position of this electron, right? That's one thing. So, and another point to remember that usually the vector r has a three component, right? X, y, and z. So once the r becomes an operator, the vector itself, then every component will also become an operator. So you have to put the hats on top of every symbol, right? Okay, that's one thing. And then we can have a potential energy operator, right? And you know, in the physical system, you can measure the potential energy. For example, if you recall in your first year physics course that, let's say we have a fixed wall, we have some spring, and then we have some mass, say m, and the spring and the mass system is undergoing in like a harmonic motion, then the potential energy, usually denoted by the V, is a function of the displacement of the mass, right, along this axis, and it is usually given by half k, spring constant is the k, x squared. So the potential is a function of the displacement x. So this potential energy operator in the quantum mechanics, you can write it like half, that's a constant, k is a constant, so nothing changed for them, but now the x needs to be written as operator form, right? X hat square, and this quantity represents that we need to operate twice with the x operator. That's it. So depending on your system, the potential energy have different expression, and there you need to put the operator expression, right? The common way, usually it's denoted by V, and then as this is a function of the coordinate, you can write it like this. That's the potential energy operator. What will be the expression? It depends on the problem, okay? The next one is the momentum operator. So in the classical physics, we have momentum P of some particle, let's say, has three components, right? Px, Py, Pz, if the motion is in three dimension. So the corresponding operator will have three components, each of which is now an operator, right? What will be the expression of the operator? I will explain these things in the next lecture, but that's another important operator. P hat, the momentum of some particle. That's a vector operator because this operator has different components, and every component is an operator itself. So once we have the P operator, then we can define the quantity called kinetic energy. You know, the kinetic energy is nothing but the P vector squared by twice the mass of the particle, right? So you can transfer this quantity as P hat squared divided by twice m in quantum mechanics. So the P, sorry, so P becomes P hat. And what is the expression for P? I will discuss these things in the next lecture, but now just remember there is an important operator known as the kinetic energy operator. So once you have the potential energy operator and the kinetic energy operator, the next operator one should look for is the important one, the Hamiltonian operator. Hamilton was a famous Irish mathematician. So the operator itself usually denoted by this H with a hat on it. And this H is nothing but the total energy of the system. So the total energy means the kinetic energy denoted by T, plus the potential energy, right? And both of them are usually sum operators. As this is the total energy operator of the systems, in some books you will see this is also represented by E hat, meaning this is the total energy operator. And the next one is like the angular momentum operator. So the model that you have in your mind, that let's say this is some center around which an electron kind of moving in a path, right? It has some velocity v, and then we can define some angular momentum L in classical physics by the position vector times the momentum of the operator, right? This is the cross product between these two vectors. So what will be the corresponding operator in quantum mechanics, right? So you need to first put hat on top of this quantity. So we have L, which is a vector operator now because we have hat here. Now R becomes an operator, also the P vector becomes another operator. So this is the angular momentum operator. In the coming lecture, we will see how to manipulate these things, but right now I just want to give you some ideas about the definition, that these are the kind of operator that we will encounter soon in the study of diamagnetism. And the last point that I want to make before I finish this lecture is that once you have the operator and a ket vector, you will always see that operators are operating on some state vector producing a state vector. So in notation, if I want to write it down, so what it means, let's say we have some operator A on the hat on it. This operator is operating on some ket vector. That's how we read this line. Some operator operating on a ket vector will give you another ket vector, for example, phi. This operator is acting from the left on this psi ket vector and producing another ket vector, right? That's what operator usually does. It operates on a state, which is a ket vector, produces another state. So, and the important point is that I'm saying it a couple of times because this operator is operating from the left, because there are other situations where you will see operators can also be acting from the right. And don't worry about that in this time, but we will see them in the future. I think that's about it. So if you want some reading about these topics that I've discussed, you can have a look in this reference from the Quantum Mechanics by Cohen-Tanuzzi. I think that's about it, and thanks for listening.